Okay, I think we'll get started. So today we're going to talk about spin pairing energy and term symbols. Now we've come off of just talking about multi-electron atoms, and the spin pairing energy will finish that story off. And then, as I mentioned last time, this idea of term symbols isn't something that we see a lot unless you're an atomic spectroscopist. But it does, I really like it as a chance to practice some of this multi-electron atom stuff. And so we'll do that just to get some real application of this. All right, well, your job has been now to practice the electron configuration or noble gas configuration. And what I hope you've seen now is that you're getting most of them right, but some of them you're not getting right when you check. And chromium is the first one, if you were just going along the periodic table, to do. If you're doing everything right, you'll get an electron configuration, and then you'll go check it, and it won't be what Mother Nature is doing. And so let's try to understand that, and we need spin pairing energy to do that. Now, we've talked about Aufbau principle, Pauli exclusion principle, and then this sort of secondary principle that can be broken, Hund's rule. And what Hund's rule says is that the electrons prefer to spin aligned. So we could go both spin up or both spin down, that's fine. But if we try to misalign the spins or pair the spins so that we have them anti-parallel, then we get something called spin pairing energy. And I'm cheating a little bit here. There is a difference between two different states and then pairing in the same state. We'll just kind of generically talking about this or this here. Regardless, there's an energy associated with that. Okay, so let's look at how we might do the noble gas configuration for chromium. So we're cruising along, we get argon, then just running through the periodic table, we should get a 4s2 and then a 3d4. Well, when we go and check the answer, it's actually a 4s1, 3d5. And what that's saying is that this state definitely exists, for sure, but it's higher in energy than this state. So usually the noble gas configurations are giving us the ground state. In this case, it's giving us an excited state. And the reason for that is that the energy to pair this electron is more than the difference in energy from taking this and putting it up here. Okay? And so the lower energy state is actually where this is unpaired, because then we don't have to pay the spin pairing energy penalty. We also, in this case, get a partially filled D shell, which is relatively stable. And all of our spins align, which optimally satisfies Hund's rule. And so the nature of spin pairing energy can help us determine the ground state. Now, chromium, you want to know, I think as a chemist you should know that. As you get up into the lanthanides and actinides, all those states are getting really close together. If you remember back to the hydrogen's energy states, they really start to pack together once N is above 3 or 4. And so you're going to get a lot of this type of stuff. Many states are within spin pairing energy. So you get a lot of exceptions to the filling rule, just following along with the periodic table. And when that happens, just know that that's a spin pairing issue. Okay, well, let's turn our attention here now to term symbols. Term symbols are even shorter hand notation than this, right? This is short. These are really, really short hand notation. And I think the best way to learn this is just through examples. So I'm going to work through some examples here, and hopefully with the 3 examples on the board, and then I'm going to do 2 more over on the doc cam, you'll get the idea and you can practice for yourself. Okay, so let's start with boron, and let's write out the full electron configuration. Now, we will see that all we really need to worry about are the valence electrons, but for now let's just write everything so that we can see where all the electrons are. 1s2, 2s2, and then 1 electron in the 2p. So, and then just as we know, the quantum number rules, so this helps us practice our rules. L equals 0 for an s, L equals 1 for a p. Well, we define this total L, this total angular momentum, as what is the largest value of L that we can make. And so let's think about these P's. We use the physicist picture now, not the chemist picture, and we say P1, P0, and P minus 1. Now, of course, an electron can be in any of these, but in the bookwork for getting the right term symbol, write these in order and then slide these over as much as you can. So in this case, we have just one P, and that's going to sit in this with the highest value here. So let's follow along here then. 0 plus 0, because S's are 0, plus 0 plus 0, plus 1, right? Now, it certainly could be plus 0 plus minus 1, but how we do this is we take the highest value possible. And so that's capital L. Now, you give the symbol that's the same as the symbol for the quantum number rules here, but in capitals. So if your capital L is 1, then your term symbol, your main term symbol is P. Now we decorate this term symbol. So let me just call this T for term symbol. We're going to decorate this up here with a, let me call it L actually. L, the degeneracy of the spin states, and then this sort of a total angular momentum, L plus S states. And so there's a J down here. And so we've gotten this first one. So L is P. Now let's get this one here. So what we do is we don't actually directly attack the degeneracy, nor do we directly attack S, from which we get the degeneracy. The degeneracy is 2s plus 1. And so whatever S is, 2s plus 1 is the degeneracy. But we actually attack it with the ms. And so these are paired, right? So in the 1s, this has to look like that. And so I get a 1/2 and a minus 1/2. I'm forced that way because of the Pauli exclusion principle. Same with the 2s. That would look exactly the same. So I get a 1/2 and a minus 1/2. Now with the P, right, I could come in like this or like that. I'm free. So I have plus or minus 1/2. So my ms is plus or minus 1/2. Well, that implies that S has to be 1/2, because just like with the lowercase letters, ms is equal to minus s, or 0, well, ms goes from minus s to s in steps of 1. So if s is 1/2, then ms is minus 1/2 or plus 1/2. So conversely, we figured out that ms is plus or minus 1/2, so that means s is 1/2. Okay, so we stick this in here. 2 times 1/2 is 1 plus 1, so 2. So now, at this stage, our term symbol is 2 superscript on this side, P. Now, sometimes people just leave this as the term symbol, but there's a bunch of states, or often is a bunch of states that are very close in energy due to the coupling of the angular momentum, spatial angular momentum, and the spin angular momentum. The total angular momentum, J, then can take on values which are the vector sums of S and L. So they can add together constructively all the way down to adding opposite of one another destructively, and then in steps of 1 from there to from here to there. And so in this particular case, L is 1 and S is 1/2. Therefore, the maximum J can be is 3/2, and then we step down in 1, so that'd be 1/2, and the minimum we can be is L minus S, or 1/2. So that's it, we're done. Now, how do we choose which one of these is actually the ground state? Well, this depends on whether we are less than half full of our subshell or more than half full of our subshell. Well, if we're less than half full of our subshell, then we choose the lower of the two. And so that gives us our final term symbol, 2p 1/2. And then we've gotten now all aspects of our term symbol. Okay? All right, well, that's how you do it. One example is not enough, so let's keep going. So let's look at carbon here. Carbon's the next one over. So now we have 2 p's. So I'll go a little bit faster through this. The S's, I need only worry about the valence shell. So that's one thing that can speed things up. The S's, 0, 0, because S is 0. And then I've pushed my p's over as far as I can, obeying Hund's rule. See, I could have put one here, but that violates Hund's rule. So obeying Hund's rule, I have this. And so I get 1, this is this 1 right here, and this is this 0 right here. So it's not 1 plus 1, because that would disobey Hund's rule. 1 plus 1, that's 1. And so this tells us that our base term is a p-type state. All right, well, here, this is the S right here, plus 1/2 minus 1/2. And now look at these. I can go, they can be up or down. And so the maximum this can be is 1. And that's really what we're interested in here. But of course it could be 1, MS could be 1, 0, or minus 1. But we want to figure out what is the maximum, and that's going to be our S value. And again, MS will imply what S is if you know all your MS values. So that means our degeneracy is 3, because 3 equals 2 times 1 plus 1. And so that gives us this symbol here. Now J is L plus S, so that's 2. And then minus 1, all the way down to L minus S, which is 0. So the possible J values are 2, 1, and 0. So our overall term symbol is 3p0 for this. Again, we're choosing, because this is less than half full, we choose the smaller J value. Okay. Well, let's do oxygen. Now we're going to be over half full. And so again, let's see. We only need to worry about the valence electrons. So we get 0, 0. Then we get 1, 1. See, there's 2 1s here now, because we're not disobeying Hund's rule. We filled this all up, and then we have 1 extra electron. So 1, 1, that gives us there. This 0 goes here, and this minus 1 goes here. So when we add this all up, we get 1. And so again, it's P. So we're running into a lot of P states. We don't want to think that all the values are P, and we'll see different states over here. But P is often one that turns up. Okay, so now we've got a lot of pluses and minuses. So this is the 2s. This set, right, are these two. They're stuck together, so they'll cancel each other. And now we have the remaining 2. And so again, we can be plus or minus 1 and then 0. So we pick the highest value. What's the highest value we can make with those plus or minus 1/2? So it'd be 1/2 plus 1/2. That's with the 2 spins up. And then that gives us an S equals 1. So our J then is 2, 1, 0, just like it was for carbon. And, well, So we think our symbol is the same, but it's a subtle difference. This is over half full, so we choose the larger of the J values. Notice there's kind of a symmetry here. So missing one electron, there's a symmetry about a half-filled shell. So missing one electron gives us the same term symbol, aside from the J, as having one extra electron. And that will hold throughout. So there's kind of a symmetry about the half-filled states. Okay, there's a bunch of examples, but let's go to the DocCam now and see a couple of more examples. We'll look up these again, and we'll kind of touch base with these. So let's try to remember these. So P2 2p 1/2, 3p0, and 3p2. All right, so here we are with the DocCam, and this is I guess it's a fairly well-known book, but I just kind of got lucky. Back in college, it was drawn from a local library, and so I grabbed it, and I'm very glad I did. Now that I'm teaching chemistry, it's a good example. It has all the almost any atomic state you would want to find. So let's look at a few of these, and then I photocopied a couple of pages so that we can write on them and see as we go here. So let's find boron, and notice it's basically every atom by their symbols, so gold and so on. In addition to the neutral atom, it also has many of the ionic states as well. So let's just choose the ones that we want to look at here. So here's boron, and hopefully you can see that. Might try to zoom in just a little, and I'll turn on the light. All right, so here's boron. What we can see here now, here is the electron configuration, and then here's the term symbol that we got. It's really tough to see. If I come in a little closer, that is a 1/2 down here, which is what we got. So let's look now. Here are these states. I'll back this up just a little now. Here are these states, and notice we chose the 1/2 as opposed to the 3/2. So here's the 3/2, here the 1/2, and they differ by an almost insignificant amount. So there's 40,000 wave numbers, because these are electronic transitions, and these are just two of these different angular momentum states. So they differ by just 15 wave numbers. So certainly at any kind of room temperature, we would be this is well below the amount of energy that would be present, but 15 wave numbers there. All right, let's look at carbon. We did carbon, and so again, hard to see, but here's our 3p0, which is what we got last time, and let's look at our states here. So 3p0, 1, 2, those were the possible J states. And again, very small. They differ by about 15 wave numbers again, and then about 27 or 28 wave numbers here. So that's carbon. All right. Let's now look. Oh, and then oxygen. So we did oxygen, and notice here now we're getting the states are inverted. Right, so 3p2. Now the states are inverted, and 2 is the largest. 2 is the symbol that we use there. Okay, let's look at chlorine. And let's walk through this. So here we are. Let's see if you can see this here. So these are the valence electrons. So these are just the inner core. So we only need to worry about these threes. And just to get our target, not that we would want to know where this, we could get this without knowing what this is, but it's going to be at 2p 3/2 is what we're going to end up with. So let's see if that's what we end up with. So we draw our S state. There's 2s, then 5p electrons. So we fill all this but one missing spot here. And so here is our S. Here's our P1. Here's our P0. And then we just have one P minus 1. And so we have 1 plus 1 minus 1. So again, here we are, another P state. Now, all these are paired except the very last one. And so thus M is plus or minus 1/2. So these are all paired. And they have to be, as we just follow our filling rules. So that implies S is 1/2. So GS is, the degeneracy is 2. And so we get 3/2 and 1/2. And we choose the 3/2 state because these are over half full. And if we go here and look at our values here, then we see the 3/2 is the ground state here, 880 wave numbers. Okay, let's do chromium. That was the one that we used as our example for the spin pairing energy. All right, so let's see. Here is the inner core. Here are the valence. And actually, this is the inner core here. This is the valence. And let's see what we end up getting. Kind of a foreshadow here. We'll finally get one that isn't a P. So remember now we had the exception. So there's a hole here, and that electron had ended up over here. Now, maybe to go a little quicker, let's just look at this. These L's will cancel out each other. So there's 2 1s, 2 0s, and 2 minus 1s. So that'll end up contributing 0. S's are 0 right away. So from this little bit, we're going to contribute 0 to L. From this bit then, the D's, well, every single one is filled with 1. So that will contribute 2 plus 1 minus 1 minus 2, 0. So we're going to get 0 plus 0 for all of this, and L equals 0, and we finally get a non-P term symbol, we get S. But there's a lot of bare states here, so this will be interesting. The S is clean, so that's plus or minus 1/2. The P's are all paired, so these are all gonna cancel out. And now the D's are all open here. And so we have 1, 2, 3, 4, 5, 6 halves, or 3 as the top value, and that's what we look for to determine S. So S is 3. Degeneracy 7. Where's that coming from? 2 times 3 plus 1. So 2s plus 1 is 7. And now J. Let's see how. Well, what is it? It's 3. L is 0, so it's 0 plus 3, and then the lowest state it can be is 3, because 3 minus 0 is 3. So there's only one J value, and that's equal to 3. And so our term symbol is 7s3. And let's go look at that. Sure enough, 7s3. There's no other states there at low energies. The next highest state then, 7,000 wave numbers above it. All right, so this is term symbols, and so it's a good chance to practice. I know it's harder to find the term symbols. There are some various tables, and so maybe you can search Google and see if you can find one that will tell you the term symbols for the various elements so that you can practice. It's always good to know, to be able to check your answer against what the actual answer is, and see how you do with your term symbols. All right, so that's it for the multi-electron atoms, and we'll start to move on now to putting these atoms together to form bonds.